Thermoconductivity affects how fast heat can transfer between two temperatures in a material. Better insulation has lower thermoconductivity. In this project, we calculated the thermoconductivity of different jackets and compared them to each other. We also tried to find correlations between thermoconductivity and different features of the jacket and a way to decide which jackets would be the best for a given surrounding temperature. The experimental portion of our project was based on the FinLab, where we used a very similar setup, but we used jackets instead of fins. The jackets were wrapped around an aluminum cylinder, and uh, hot air was passed through the heat gun through the aluminum cylinder, and the temp and temperature measurements and velocity measurements were taken so that the heat flux and consequently the thermoconductivity could be calculated. We needed to get temperature measurements at different places of the setup to calculate values required for calculating the thermoconductivity. We measured the exit temperature of the air to calculate the mass flow rate. We measured the surface temperature of the cylinder at either ends to get an estimate of the temperature difference of the air. Finally, we measured the temperature on the inside and the outside of the jacket at the middle of the cylinder to use the formula on screen to get the overall heat transferred. We used the resistance method to find the thermal conductivity of the jackets from the values obtained so far. We approximated the jacket to be a cylinder with thermal conductivity K, which would relate to the thermal resistance of the jacket. By using the temperature measurements on either side of the jacket, we were able to relate the thermal conductivity to the heat transferred. Thus, we obtained a value for the thermal conductivity for each jacket tested. The different thicknesses of the jackets and the different heat fluxes caused by them led to different thermal conductivities. The Burton jacket, which was made up of polyester entirely, had the lowest thermal conductivity and consequently was the most insulative. The black vest jacket, made up of duck down, had the highest thermal conductivity and was the least insulative. Between those two extremes, we had different jackets made up of different materials, including cotton, duck down, and polyester. We wanted to estimate the thermal conductivity of the jacket without having to do the experiment. We started by taking a weighted sum of the thermal conductivity of each material used in the jacket based on the amount of the material in the jacket. The results from this method vary wildly. As seen in the table, the error in the fleece jacket estimate was only 2.4%, but the error in the Burton jacket estimate was almost 840%. We also tried to make power law, linear, and parabolic curve fits of the thermal conductivity with respect to different aspects of the jacket. We tried to model how the thermal conductivity changes with varying polyester, down, and cotton content, as well as the thickness of the jacket. However, we were not able to find a clear correlation between the thermal conductivity and these properties. Now, we wanted to find the best set of jackets to wear for a given surrounding temperature. We had to make some simplifying assumptions to be able to do so. We modeled the human body as a cylinder of diameter of 30 centimeters. We found that the average heat flux from a person who is walking at 1.5 meters per second is 150 watts per meter square Kelvin. We wanted to keep the person at a constant 37 degrees Celsius, and so we assumed steady state conditions. We also assumed that there was no energy stored in the jacket, so all the heat that was produced by the person would have to go out through convection. We also neglected radiation and assumed that the air outside was still. We wanted to find how much heat is being lost to conduction from all possible combinations of jackets. We also use the resistance method in this case. To find the overall resistance of a set of jackets, we added all the individual conductive resistances of the jackets together. Since we assumed that the jackets are also cylindrical, the order in which the jackets were placed mattered, and so we had 13,699 combinations, unique combinations of jackets. We also needed to get the convective heat transfer coefficient H, and since we did not know the surface temperature of the outside of the jacket, we had to guess the film temperature. Using this guess, we went through the process of finding H for external convection and iterated 10 times to converge onto a solution. Using this H, we were able to calculate the heat transferred out of the jacket set. We used some tools in Python to automate the process of finding all possible combinations of jackets and the air properties for every set of jacket. The heat flux calculated for each set of jacket was stored in an array, and the difference between each heat flux and the optimal heat flux of 150 watts per meter square Kelvin was calculated. The set of jackets with the smallest difference between these two values was taken to be the best jacket for that surrounding temperature. Let's do a quick demo. So I'm going to run the program, and it's going to ask me for the temperature in degrees Celsius. It's -7 degrees right now. It's going to take a while to compute, so I'll fast forward to when it calculates the answers. So according to the program, the fleece jacket and my jacket, in that order, would give us the best, um, would keep us most comfortable. Um, this combination would produce a heat flux of 149 watts per meter square Kelvin, which is pretty close to the optimal heat flux of 150 watts per meter square Kelvin.